Hi everybody. For the analysis one for the first year university, chapter 2, sequences of real numbers. Definition of a sequence. A sequence of real numbers noted by xn from n equal 1 to infinity is a function f from n or a subset of n into r, the real numbers. F associate for every natural n, f of n, the image, equal a real number x n for n equal 1, 2, etc. xn is the general term or nth term. For examples, example 1, let the set xn of numbers minus 1 power n plus 2 power n between 1 and infinity. xn, that general term, for n odd minus 1 power n equal minus 1 plus 2n. If n is even, minus 1 power n equal 1, xn equal 1 plus 2 power n. Example 2, consider the sequence un of real numbers such that un equal in terms of n 1 over n plus 1 plus 1 over n plus 2 plus etc. plus 1 over n plus n equal to n. Example 3, un such that the first term u1 equal 1 and the relation between un and un minus 1, un equal 4 minus un minus 1 over 3 minus un minus 1. This is a recurrence relation between two consecutive terms, n minus 1 and n. Example 4, consider the sequence un such that the general term is n factorial over 2n plus 1, with n factorial is 1 times 2 times 3 times etc. times n. For the sequence xn, we say that xn converges to a real number L is equivalent to, for every real number epsilon positive, there exists n0 belongs to n such that for n greater than n0 يعني after an order n0 we have xn minus L in absolute value less than epsilon. Practically we find n0, we must find n0 in terms of epsilon. To every epsilon we find n0. n0 depend of epsilon. We write limit xn as n tends to plus infinity equal L. Limit of xn equal L if xn converges to L. L, the limit, is unique. The sequence xn is divergent in two cases. First, if the limit xn as n tends to plus infinity equal infinity. L is infinity. We say that xn is divergent. Or xn has no limit. For example, if xn equal minus 1 power n, for n odd, we have xn equal minus 1. If n is even, xn equal 1. If the sequence xn is convergent, then xn is bounded. Example, show that limit as n tends to plus infinity of n over n plus 1 equal 1. By definition, we must prove that for every epsilon positive, there exists n0 belongs to n, such that for n greater than n0, we have xn, which is n over n plus 1 minus L minus 1 less than epsilon. We take this inequality and we find n in terms of epsilon. Absolute value of n plus 1, n minus n minus 1 less than epsilon, or minus 1 over n plus 1 less than epsilon. Also, absolute of minus 1 is 1 over n plus 1 less than epsilon. So n plus 1 is greater than 1 over epsilon. Finally, n greater than 1 over epsilon minus 1. So we choose n0 greater or equal 1 over epsilon minus 1. So for every epsilon positive, there exists n0 belongs to n, such that for n greater than n0, we have xn minus 1 less than epsilon, so limit of n over n plus 1 equal 1. n0 is any natural greater or equal 1 over epsilon minus 1. We consider any real number epsilon positive, and we find n0 in terms of epsilon. Remarks: if the sequence xn is of positive numbers, means that xn greater or equal to 0 for every n, and if limit of xn equal L, then the limit is greater or equal to 0. Similarly, if xn less than or equal to 0 for every n belongs to n, and limit equal L, as n tends to plus infinity, then L is less than or equal to 0. If the terms are positive, the limit is positive, and if the terms are negative, the limit is negative. We say that xn is bounded if there exists m strictly positive, such that the absolute value of xn is less than or equal to m for every n belongs to n. xn is bounded above if there exists m belongs to R, a real number, such that xn less than or equal to m. xn is bounded below if there exists m belongs to R such that xn greater or equal to m for every n belongs to m. Now we have the theorem: if the sequence xn converges, then the sequence xn is bounded. In fact, xn converges, let L equal the limit of xn as n tends to plus infinity. By definition of the limit, we have for every epsilon positive, there exists n0 belongs to n, such that for n greater than n0, we have xn minus L less than epsilon. we must find M belongs to R or M strictly positive such that absolute of xn is less than M. We must find M. We use the equality xn absolute xn minus absolute L is less than or equal of absolute xn minus L. Absolute xn minus absolute L less than or equal absolute of xn minus L. So absolute of xn minus L less than epsilon implies absolute xn less than absolute L plus epsilon. Absolute xn minus absolute L less than epsilon, so absolute xn less than L plus epsilon. And we take M equal absolute L plus epsilon. Absolute xn less than M, so xn is bounded. For example, find the limit of the sequence un if the general term is un equal n over n2 plus 1 sine n. We know that sine n is between minus 1 and 1. We can divide by the positive number n squared plus 1 minus 1 over n2 plus 1 less than sine n over n2 plus 1 n2 plus 1. We can divide by a positive number the inequality. Now we can multiply by n. N is positive. We obtain the same inequality, same sense. So minus n over n squared plus 1 n sine n over n2 plus 1 n over n2 plus 1. We know that the limit of n over n2 plus 1 as n tends to plus infinity is 0, is the same of the limit of 1 over n. 1 over infinity is 0. Similarly for n over n2 plus 1. n over n2 is 1 over n, tends to 0 if n tends to plus infinity. Therefore, n sine n over n2 plus 1 tends also to 0 as n tends to plus infinity. N over n2 plus 1 sine n is between two terms, each one tends to 0, then this quantity tends to 0. We can write limit un as n tends to plus infinity equals 0. Second example, if alpha is strictly positive, then limit of 1 over n power alpha as n tends to plus infinity is 0. Using the definition. The definition of a limit equal L, so we must use the definition for every epsilon positive. There exists n0 belongs to n, so that if n greater than n0, we have un 1 over n alpha minus the limit is less than epsilon. We must find n0 in terms of epsilon. We use the inequality 1 over n alpha minus 0 less than epsilon. So 1 over n alpha, the absolute of 1 over n alpha is 1 over n alpha, since 1 over n alpha is strictly positive, less than epsilon. We can find n in terms of epsilon. Alpha is given. So n alpha is greater than 1 over epsilon. The inverse of 1 over n alpha is n alpha greater than the inverse 1 over epsilon. N is greater than root alpha of 1 over epsilon. So we can take n0 greater or equal to root alpha of 1 over epsilon. For every epsilon, there exists n0 equal radical alpha of 1 of epsilon such that n greater than n0 implies 1 over n alpha minus 0, the limit, is less than epsilon. So we have limit n, if n tends to plus infinity, of 1 over n alpha is equal to 0 for every alpha strictly positive. We have a second rule for the limit. If alpha is strictly positive, then limit as n tends to plus infinity of radical n alpha is equal to 1. For every alpha strictly positive, radical n of alpha tends to 1 if n tends to plus infinity. We have three cases. If alpha equal 1 greater than 1 or less than 1. If alpha equal 1, we have radical n of 1 is 1 for every root n. Now, if alpha is strictly greater than 1, we put a n equal radical n alpha minus 1. If limit radical n of alpha equal 1, so radical n alpha minus 1 is strictly positive. The limit equal 1, so radical n alpha is less than 1. Then radical n alpha minus 1 is strictly positive. So an plus 1 equal radical n alpha. Now we can use the binomial theorem . 1 plus an power n is less than or equal 1 plus n an. One plus an is less than or equal 1 plus an